You guys have just gotten done watching some videos on the Fibonacci sequence. Fibonacci sequence is really cool. It shows up all over the place in nature, in mathematics, in geometry, and architecture. Lots of cool things develop from the Fibonacci sequence. Now I'm going to look at something a little bit new. It's called Pascal's triangle, but it's going to relate slightly to the Fibonacci sequence, as you'll see in a few minutes. So here's the idea of the Pascal's triangle. There's this thing called a binomial expansion. So let me explain what that is first. If you take, and some of you may have seen this before, if you take like x plus 2 times x plus 2, just two binomials. Binomial is two terms, right? Bi means two. Two terms, and you multiply them together. Some of you have seen this. You've probably heard the FOIL method before. Essentially, the idea is it's an expanded distributive property where every term on the left has to multiply every term on the right. So you take the x on the left, multiply by the x and the 2 on the right. Take the 2 on the left, multiply it by the x and the 2 on the right. And you get what we call the FOIL method. It means FOIL stands for first, outer, inner, last. So you take the first two, multiply them, the outer two, the inner two, and the last two. Okay, so first, outer, inner, last. And that's nice for two binomials multiplied together. And when we do that, x times x is x squared. X times 2 is 2x. 2 times x is 2x, and 2 times 2 is 4. And then we combine like terms, and we will end up with x squared plus 4x plus 4 in this case. Okay. Well, we can expand this to a more general situation. What we typically do is we're going to replace the x and the 2 because those are a little more specific. We'll say these two terms could really just be anything. We'll call them a and b. So we have a plus b times a plus b. And now if you distribute that, or FOIL method, you get a times a is a squared, a times b is ab, b times a is ab again. Now the order of the factors doesn't matter because multiplication is commutative. So a times b and b times a, they really mean the same thing. And really I just wrote a times b again because it didn't matter. And then b times b is b squared. Right, and that gets all four. Whoops, I didn't write that one in. There, gets all four combinations. Notice the two in the middle are like terms. They both have an AB. And so it's 1AB plus 1AB makes 2AB. All right, so that's a squared plus 2AB plus b squared. Okay? Now that's cool for a binomial times a binomial, right? A plus b times a plus b. Let's say I wanted to throw a third one in there, right? So let's say I wanted to do, now I'm going to need a little bit more space. And I'll switch colors here. So let's say I wanted to do, well, a plus b times a plus b times a plus b. Throw a third one in. Well, I know these first two already make that expression, a squared plus 2ab plus b squared. No need to repeat that. But then I have to multiply that by the a plus b at the end. And so again, the distributive property generalizes. Now I can't really call it the FOIL method because I've got too many terms here to really do the FOIL with, the first, outer, inner, last. But what I can say is every term on the left has to multiply every term on the right. So we're going to have 6 combinations this time, 3 by 2, okay? And you'd have a squared times a is a cubed, a squared times b is a squared b, 2ab times a is 2a squared b, right? There's a couple a's there, so we call that a squared. 2ab times b is 2ab squared. Right, that gives me my first 4 combinations. Then I got b squared times a, and that's ab squared. And a squared times b is just b cubed. I almost said a there. B cubed, okay? And now if I look for my like terms, a squared b and a squared b, those two terms are both a squared b. I have 1 and 2 make 3, so that's a cubed plus 3 squared b. And then I have a 2ab squared and an ab squared, so it's 2 and 1 of those make 3 again. So that's plus 3ab squared, and I've got my b cubed in there as well. All right, so that obviously gets longer, right? I went from 3 terms to 4 terms. If I were to put another one in there, if I made it a plus b times a plus b times a plus b times a plus b, 4 of them, then I'd have another term added on, and then more and more and more and more, right? So the more times you multiply by a plus b, the longer the final expansion is. Now this is what we call the binomial expansion. It's a binomial, and then you expand it. Now repeated multiplication like this can also be represented by an exponent. So a plus b times a plus b times a plus b is really just a plus b cubed. There's 3 of them multiplied, right? Similar over here, if I just did a plus b times a plus b, that's really a plus b squared. And so what we're really doing is we're raising a binomial to a power. The bigger that power is, the longer the expansion. So a binomial expansion, is just this idea that you raise a binomial to a power and multiply it all out. When you do that, you get this long polynomial. Now, the polynomial gets huge when you start getting larger powers. If I put a 15th power in there, right, you got a plus b, da 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 da, 15 times, and you just keep distributing all that out, you get a huge expansion. But there are some cool ways to determine the pieces of that expansion. And what I really want to focus in on are the coefficients. Coefficients are the numerical part of each term. For instance, on the a plus b squared, the coefficients are 1, 2, and 1. Right? Those are the numerical parts of those 3 terms. With the a plus b cubed, the coefficients are 1, 3, 3, and 1. Right? Now let's take this back a step. We'll start from the beginning. Let's start from a power of 0, and we'll do a power of 1, and then 2, and then 3, and we'll start looking at all these coefficients as we go. I'm going to leave a couple of those up here, but really all I really want are the coefficients, a list of coefficients. All right, so let's take the first one. That would be a plus b to the 0 power. That's kind of your first exponent, your starting point. Well, that's just 1. Right? Anything to the 0 power is 1. That's a property of mathematics, right? Property of exponents. If I did a plus b to the 1 power, well, anything to the 1 power is just itself, right? A plus b. Now notice, if I make a list over here of the coefficients, the first expression has just a 1. This one is a 1 and a 1, so it's a pair of 1s. Okay? What I'm going to do is I'm going to form a triangle, and it will work out nicely. The number of terms works out perfectly for this. If I do a plus b squared, we've already seen that one. It's 1, 2, 1, right? So it's a squared plus 2ab plus b squared. So it's 1, 2, and 1. Notice it's always going to be 1s on the outside of this triangle, right? The first term and the last term are always coefficient of 1. The middle term, or this term in the middle here, happens to be the sum of the 2 above it. It's kind of interesting. Is that just by chance, or is there a reason for that? Let's see what happens here. If I take the third one, if I did a plus b to the third, I already know what that is. I'm not going to rewrite it. But it's 1, 3, 3, 1 are the coefficients. So 1, 3, 3, 1. And notice again, 1's on the outside. The 3's are the sum of the 2 numbers immediately above it. Okay? If I were to continue the pattern, which I'm not going to show you all the details because it just gets to be tedious, But if I continue the pattern, that pattern of summing up the numbers above it will continue. It's kind of cool. It can be proven. I won't do that right now. But it has to do with the way these develop as you add more and more factors in. Okay? And so, what we end up with, if we do a plus b to the fourth power, well, that gives us a row of 1. Now 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and then a 1. There's also going to be some symmetry to this, right? You're going to see, you know, the first half of each row is the same as the last half, essentially. Here I've got 1, 3, and 3, 1, kind of like a palindrome there, reverses of each other, right? Here it's 1, 4, 4, 1, and then you've got the number in the middle because it's odd. You can't really duplicate that one, right? There's an odd number of numbers there. So we're going to have this pattern continue, and the next row would be 1, and then 1 and 4 is 5, 4 and 6 is 10, 6 and 4 is 10, 4 and 1 is 5, and I'm running out of room, but there's a 1 on the end down there. Okay? And then so forth. And so for every power that you have, the number in that row, the numbers in that row are calculated by putting 1s on the ends and then adding up the digits immediately above, the 2 digits above the next one down, right? So you can see how I'm positioning those in between digits in the next row, okay, or in the previous row, I mean, okay. If I wanted to do, you know, a plus b to the 15th power, well, I would have to run this all the way down to the 15th row. Now, there are actually ways to calculate these things without having to run the whole triangle out. I'm not going to show you those. They're actually really cool counting tricks, but we're not going to cover those in this course. What I would do then is I need the row that starts 1 and then 15 and ends down in the end with a 15 and a 1, because it's the 15th power. So the second number in is always that power. Obviously, you're just adding 1 to the previous row, right? So that works out to get that. You know which row you're going to hit. Then you just need to calculate down to it. Okay. Now, what's pretty cool about this Pascal's triangle? So this is what we call Pascal's triangle. It's the triangle built up by adding the previous the numbers up above to it. What's cool about it, I think, there's lots of cool things in this triangle. There's an activity I'm going to have you guys do on e-learning. There's a worksheet where you're going to build this triangle into a sheet of graph paper. Okay, I put a sheet of graph paper, I don't know if you can tell that's graph paper, but it is. I put a sheet of graph paper in e-learning with the worksheet. I just took a picture of this thing and saved it as a PDF and put it on there. So you have graph paper. What I want you to do is kind of tip that graph paper and start up in the top corner. So I don't know if you can see, this is on a 45-degree angle roughly. Start up at the top corner and put your 1 and then your 1, 1 and then your 1, 2, 1 and keep going rows this way so that your graph paper will kind of form. This is your corner, and then here's a row of grid of your grid, here's a row of your grid, here's a row, and so on. And then let's see, there's going to be a row going down this way and this way, this way, this way. Okay, so you get that's what your graph paper will look like. What I want you to do is fill the whole graph paper in, the whole thing. Okay, now it gets a little bit ridiculous to write these numbers in, because as you add these up, the numbers get huge. By about the 10th or 11th row, you can't even fit the numbers in those boxes. So what I really want you to do when you get it all done, and I'll explain as a shortcut, I want you to shade in all of the odd numbered all the odd numbered squares in the grid. Okay, so you're going to color them in. I don't care what color you use, just pick a color, and you shade in all the odds. So like the number 1 here, 1, all these, anything with a 1 in it, anything that's odd, right? So 1s get shaded in, the 5, the 3, this 5, and so on. You go all the way down the list, just shading in the odds, okay? Shade in odds. So you don't actually have to fill in the number all the way down the list, because obviously you won't fit them. They're just, the numbers get too big to fit in the boxes. All you need to do is know how to calculate odds and evens. How do you know if the next row is going to be an odd number or an even number in each box? That's an exercise I'm going to leave up to you to decide. You might be able to figure it out just from what I have up here. And if you don't know, I'll try a few things. See if you can figure that out. That's one of the questions I'm asking on the worksheet is, how do you know whether, when you add two numbers, whether you get an even or an odd? Kind of interesting. And then I want you to just fill in all the way down, after you get, I don't know, 9, 10 rows in, just fill in whether it's going to be even or whether it's going to be odd with an E or an O. That'd be enough, okay? You don't need to actually put the number in there, just an E or an O. And then shade in all of the O's, okay? They're the odd ones, okay? And then you'll get a really cool pattern, and then I ask you to describe what that pattern is. I also ask you to give the binomial expansion for one of these. I think it's the 7th power or 8th power, one of those. I just wrote the worksheet. I don't remember what I put in there. I think it's the 7th one, okay? And so there's a few questions on the back of the worksheet that I want you to work through, namely determining odds and evens, going through the expansion for the, I think it's the 7th one down, and then also describing what pattern you get once you've filled in the entire graph paper. I also want you to submit the graph paper. So you're going to submit answers to the 3 questions and the graph paper into the assignment on e-learning called Pascal's triangle. Okay. Now, how does this relate to the Fibonacci sequence? Well, let's take a look at what happens if I take this Fibonacci triangle and I right align it. You heard of right aligning things on your computer maybe. It just means shifting it so that it's all lined up on the left. Did I say right? I meant left. Left aligning on the left side. Sorry, because I'm looking at my phone screen here. It looks on the right to me. Everything's backward. No, I'm good. Okay, left aligning it. Here we go. So the first one is a 1, then it goes 1, 1. So I'm going to left align 1, 2, 1, 1, 2, 1, 1 through 3, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 5, 10, 10, 5, 1, and then I won't go through all the details after that, but where Fibonacci sequence comes in is if you take diagonal entries here. If you add up diagonal, that's a 1. I should do this in another color so that it pops. It stands out from the rest. Let's do this in, I'll do it in black because the red will smear funny. So there, add those two, add that together, it's just 1, right? Add that one, that's a diagonal, that's 1. 1 and 1 makes 2. 1 and 2 makes 3. 1, 3 and 1 makes 5. 1, 4 and 3 makes 8. There'll be another 1 down here, so it's 1, 5, 6, and 1 makes 13. And you can see on those diagonals going up that you end up with the Pascal, or with the Fibonacci sequence, right? 1, 1, 2, 3, 5, 8, 13. Next one would be 21, and then it would be 21, and 13 is 34, and then 55, whatever it is, right? 21, 34, something like that. Anyway, yeah, so it just keeps going. The Fibonacci sequence appears on all these diagonals if you add up the numbers on the diagonals. So just kind of cool connection. There are many other really cool things with Pascal's triangle. I'm having you guys practice one where you shade in the odds. You could shade in things like multiples of 3 or other types of numbers as well. And you get other geometric patterns, but some very cool patterns end up showing up with the Pascal's triangle. Some cool things here. So neat geometry, neat arithmetic, some algebra involved, and they all come together very eloquently with Pascal's triangle.